Hello, today we are going to be taking a look at the problem Farmer John's favorite operation. Let's look at the problem statement. Alright, so here we have our problem. It is another cold and boring day on Farmer John's farm. To pass the time, Farmer John has invented a fun leisure activity involving performing operations on an integer array. Farmer John has an array A of n up to 10 to the power 5, non-negative integers, and an integer m. Then Farmer John will ask Bessie for an integer x. In one operation, Farmer John can pick an index I and subtract or add 1 to AI. Farmer John's boredom value is the minimum number of operations he must perform so that AI minus x is divisible by m for all I between 1 and n. So among all possible x, we need to output Farmer John's minimum possible boredom value. Now we have some test cases, but I'm actually going to share my initial solution approach and then sketch these out because that will make the sketch make more sense. So at first glance, I'm thinking surely we can map this out. So my approach initially is to take everything mod m, subtract each possible x, and for every x, check what the minimum sum of the remainders is. So I have this illustrated here. We have our numbers, and then I took everything modulo 9, which essentially is just find a remainder when divided by 9. And then I already tried some possible x values, and after trying all x values you can, you see that the best possible x is going to be free. So I subtracted free from each term. Then I added up the absolute values. And because I'm adding up the absolute values, I can take care to ensure that I'm minimizing the absolute value. Because the remainders are circular, a remainder of 5 is going to be the same as a remainder of -4. And I encourage you to check out some basic modular arithmetic resources to find out why. But for that reason, I'm going to rewrite the remainder of 5 as a remainder of 5 minus 9. And summing up those absolute values gets you 11. So that's our sketch of the sample test case. And that seems simple enough, but that's going to be problematic if we're doing it for all x's. So to optimize, we're going to analyze the function a bit. Each term cost as x is essentially a triangle wave. So we have a 0 at x equals ri, peak at ri plus m plus over 2, and then we go back down. So therefore, each term only bends at exactly 2 points. The summing the n triangle waves gives a function that can only bend where at least one individual term bends, at most 2 endpoints total. And between 2 consecutive bend points, the total cost is going to be a straight line, and a straight line's minimum is always at an endpoint, never the interior. So this makes us narrow our candidates by a lot. But how do we test them? The key thing is we're going to sweep our candidate x values instead of searching for one. So the true minimum must sit at one of at most 2 n candidate x values. So we're going to track a slope delta at each candidate point. So +2 at a valley and -2 at a whole number peak. And when m is odd, the peak will land on a fractional point. So we need to be mindful to split it into 2 adjacent integer points instead of one point getting the full swing. And then we sweep across all candidates left to right, extending the cost linearly between points using the running slope and tracking our minimum. Now we just need to find the minimum across your sweep. So that's the algorithm. But of course, no problem goes without its own debugging issues. So when implementing, I had quite a few bugs to squash. So first of all, I was computing the 2 peak points independently with separate branches, which silently collapsed onto the same integer rather than landing on 2 distinct adjacent ones. So the fix for this was to compute both points from one fractional peak value using 4 and 4 plus 1 instead of 2 independent branches that could land on the same integer. Bug 2 was the missing wraparound. The sweep never covered the stretch back to x equals 0, skipping the minimum hiding in that final region. So the fix was to add a final step after the sweep that applies the last point slope and extends cost across the remaining gap back to x equals 0. Finally, I used the shortcut formula to estimate the starting point, which broke quietly when a peak pair surpassed the m-1 0 boundary. So the fix was to compute the entering slope directly as cost 0 minus cost m-1 instead of guessing each term's direction from a raw comparison to m over 2. So this all was caught because I stress tested my code. Alright, so let's take a look at the code. As always, I read in our input using the cat.io class, which I will link in the description below. And then as I read in the input, I notice that only the remainder matters. So I just take the modulo m to begin with. We discussed the piecewise linear thing already in the algorithm. And I store all the inflection points in this map. So for each number in the array, I'll put that point and its slope. So if the value and slope flips from -1 to 1. So the old buggy version of this block was this, which ran two separate branches, and for some A, they'd both land on the same point instead of two different adjacent ones. So the fix was to get both points from one fractional peak value, else it's just going to be a single peak because m would be even. Then I anchor the sweep start at 0, 0, and I keep a list of our points, which are just going to be the keys of our inflection map. Okay, and then I sort these, pretty straightforward. And then I keep a running cost function. So I sum up the costs over all the points in the array, and I take the minimum of the remainder and m minus the remainder for a reason that we initially outlined when discussing the test case. Okay, so then the old buggy version of the starting slope was I tried to add 1 or -1 depending on if the a was greater than or equal to m divided by 2. And this looked reasonable, but it silently broke for whichever term's peak pair happened to straddle this m-1 over 0 wraparound. Because that term is actually flat there, not going up or down. So the fix was just to compute the real slope directly, without any guessing. So I am actually computing the slope here. So that's our starting slope. And then I take the running cost, and then I calculate, okay, what's the cost at this x? So this is what that loop's doing, and then this used to stop here, never loop back to x equals 0. So I had to do one more iteration after the loop ended, and then I printed the best. So yeah, that's the code. And I have linked this in the description too. Alright, so let's see if this works. Alright, so we have our file uploaded. This one was standard IO, so I didn't need to change it to file IO. And our grading is in progress. And would you look at that? Our code is running. And it's passing our test cases. So let's just give it a minute. This one did run a bit slower. But, I mean, thanks to our Java multiplier, it passed. So, yeah, we did the problem. We did it correctly. And now let's go into some takeaways from this problem. Alright, so here we have two main takeaways. So one was a piecewise linear insight. When a cost function is built from simple repeating shapes, the search space often collapses from everything to just the bend points. So you rarely need to check every value. And then verify, don't assume. A shortcut formula can look right on sample cases and still be silently wrong at a specific boundary. Brute force stress testing catches what tracing my hand misses. So that is the end of this problem. Comment if you have any questions. And yeah, thanks for watching.